Hey everyone, exciting news! Just a few weeks after DeepSeek unveiled their most powerful open source large language model for general purpose, that is DeepSeek V3, today they have released an open source alternative to O1, DeepSeek R1. It is the closest match to the reasoning performance of OpenAI's ChatGPT-o1. DeepSeek has released a series of R1 models along with a technical report. Previous studies have attempted to replicate ChatGPT-o1, but their processes are quite complex. They use process-based reward modeling, reinforcement learning, search algorithms like Monte Carlo tree search and beam search. Those methods are quite complicated, but the results are not very ideal. In contrast, DeepSeek employs a more elegant and concise reinforcement learning approach to achieve this goal. So today I'm going to show you how DeepSeek R1 is implemented and demystify its workings. Alright, here is the outline. Today I will cover three main aspects: the performance, the model releases, and mainly the methodology behind how they trained this model. Now let's start by looking at the performance. As you can see here on various reasoning benchmarks, DeepSeek R1 represented by the dark blue bars, while OpenAI O1 December 17 is shown in dark green. On about half of the benchmarks, DeepSeek R1 outperforms O1, while on the other half it trails behind. Overall, it's slightly below O1, and the smaller version R1 32B based on Qwen 2.5 32B has performance comparable to O1 Mini. Now let's discuss their releases. So they have released three types of models: DeepSeek R10, the large model with 685 billion parameters, DeepSeek R1, and a series of distilled R1 models. So let's examine them one by one. DeepSeek R1 0 is trained solely with reinforcement learning, without relying on supervised fine-tuning. Despite this, it still showcases impressive reasoning capabilities, including self-verification, reflection, and generating long chain of thought. This is quite surprising considering previous methods as I have mentioned earlier, required a variety of manual approaches to achieve these capabilities. But they achieve it simply through reinforcement learning without even asking the model to behave like those. And it's also the first open research to validate that the reasoning capabilities of large language models can be fostered purely through reinforcement learning. However, its weakness lies in poor readability and language mixing. In its output, there is mixing of languages, probably switching between Chinese and English. To address this, they developed an improved version called DeepSeek R1 without the 0. It utilizes a small amount of code starter data and multi-stage training pipeline, including 2 reinforcement learning stages and 2 supervised fine-tuning stages. So this model overcomes the weakness of R10 and achieves better reasoning and general purpose performance. They also distilled R1 into Qwen and Llama models ranging from 1.5 billion to 70 billion parameters. Their 14 billion parameter version of Qwen outperforms the 32 billion parameter preview reasoning model released by the Qwen team. And this model can run on consumer GPUs like RTX 3090 or TUL 3090. Okay. Next, let's discuss the methodology. So let's start by talking about how DeepSeek R10 is trained. It is trained using reinforcement learning. The specific method used is called Group Relative Policy Optimization. This is a variant of Proximal Policy Optimization, PPO. It doesn't rely on a critical model or a value function model. So this is the difference. And the objective function here might look a bit complicated. I will break it down for you. So here Q is the questions sampled from distribution PQ. So this means there is a pool of questions, and they sample question from this pool, and they generate G answers. Each one is denoted as OI. And the answers are generated using an older version of the policy model, not the up-to-date one. So the overall idea of this reinforcement learning is to train the model to generate to more likely generated answers with higher rewards and less likely generate answers with lower rewards. And the rewards here are represented by AI, which is the advantage of answer OI compared to the average rewards of all sampled answers. So here is the equation 3. Ri represents the total rewards from the answer OI minus the average reward of all G answers. And if it's larger than the average, it has a positive advantage, and it's normalized by the standard deviation. However, the answers are generated by an older policy, not the up-to-date policy that is trained. So they need to use a technique called importance sampling. This is a commonly used approach where answers are not generated using the latest model. Instead, a slightly older version is used. This is because they want to train the new model on the generated data for multiple epochs. This will improve the computational efficiency during training, comparing using the up-to-date model to generate the new data and train for only one epoch. Therefore, the distribution of the old and new policies are slightly different. To address this, the importance sampling is used. In PPO, it's also used. So importance sampling is represented here as a ratio. It's probability of the new model generating the answer OI over the probability of the old policy generating OI. This adjustment aligns the training with the probability distribution of the new up-to-date model. So overall importance sampling allows us to generating the training model for the up-to-date model using an older version. And the clip here refers to clipping the importance sampling ratio. This is because we don't want the importance sampling ratio to vary too much. If the ratio is quite different, then quite different from one, that means the old and new policies diverge significantly, causing importance sampling to be ineffective. And additionally, subtracting the KL divergence between the current model and the reference model ensures the new model's behavior doesn't deviate too much from the reference model. This is similar to what's done in PPO or DPO to prevent the model from collapsing when it diverges significantly from the reference. Next, let's discuss the reward modeling. So we need to ensure that we reward model appropriately to incentivize the desired behaviors. For math problems, the reward is based on the correctness of the final answer. So the model is prompted to generate a final answer after the chain thought, and then it is compared to the correct answer. And for programming problems, they use lead code challenges. So they compile the code generated by the model and run it against a few test cases to determine the correctness. And yeah, so based on the result, there is the reward. And they also encourage the model to follow a specific format by replacing its reasoning between the think tags and put the generating answers afterwards in the answer tags. And if the model adheres to the format, it receives a positive reward. They don't use a process-based neural network reward model here because it could better handle problems that require nuanced evaluations. And in reinforcement learning, there is reward hacking. So they want to avoid this kind of problem. And here is the final template they use. So the prompt instructs the model to generate both the answer and the reasoning processes. And here are the results. As you can see, DeepSeek R1 trained solely with reinforcement learning performs better than O1 mini and slightly worse than O1 September 12 on multiple benchmarks. Additionally, using a majority voting where multiple answers are generated and the most common one is selected as the final answer yields much better results. And on some benchmarks, majority voting makes the R1 model outperforms the O1 model. And the diagram shows that as the training progresses, the accuracy improves with the training steps. And it also shows the average length of the response increases. So the authors didn't explicitly encourage longer responses, but surprisingly, the model automatically learns to generate longer answers to improve the accuracy. Thus, the performance of R1 demonstrates robust reasoning capabilities without supervised fine-tuning, highlighting the model's ability to learn and generate effective reasoning chains through reinforcement learning solely. So, is reinforcement learning all you need? Not exactly, but it's surprisingly effective. And additionally, certain behaviors emerge spontaneously, such as reflection, where the model revisits and evaluates its previous steps, and the exploration of alternative problem-solving approaches. So in previous O1 replication studies, researchers tried to encourage those behaviors by using methods like Monte Carlo tree search or beam search. However, they found that these behaviors could arise naturally without such techniques. So this is quite surprising. Now let's discuss DeepSeek R1. The model addresses the readability and language mixing issues found in R1 and aims to further improve performance and accelerate convergence by incorporating a small amount of high-quality data. They also want R1 to not only produce chain of thought, but also demonstrate strong general-purpose question answering capabilities. They collected a small dataset of long chain of thought through 3 methods. Using few-shot prompting with long chain of thought as examples, directly prompting those base models to generate answers with reflections and verification, and gathering R10's outputs in a readable format. Human annotators then refine those results through post-processing to ensure quality. And during the supervised fine-tuning, they employ slightly different format. So they use a special token to separate the reasoning process from the final summary. And and after the supervised fine-tuning, they applied reasoning-oriented reinforcement learning, similar to how they trained R10 with GRPO. And the difference here is that they also reward language consistency. That is, the proportion of the target language words in the chain of thought serve as a signal, reward signal. And this led to a slightly decrease in performance, but made the chain of thought and final answers more readable. And the final reward combines the summary accuracy with the language consistency. And in the second stage of the reinforcement and supervised fine-tuning, they used the rejection sampling to curate 600K reasoning data points. They generate reasoning trajectories using the model trained from the previous step, and applied rule-based evaluation and DeepSeek V3 for evaluation. So rule-based evaluation checks if the answer matches the correct ones, and they employ DeepSeek V3 here without worrying about the reward hacking, because this is not a reinforcement learning step. This is a supervised fine-tuning step. And they filter out incorrect trajectories and those with mixed languages or overly long paragraphs. So this process resulted in 600K high-quality reasoning data. And additionally, to enhance the general purpose question answering capabilities, they created 200K non-reasoning data for tasks like factual question answering, self-cognition, or translation. And they used the DeepSeek V3 pipeline and reuse portions of their supervised fine-tuning data to train this model. And I previously made a video introducing DeepSeek V3, so you can check out on my YouTube channel. And for the non-reasoning data, they prompted DeepSeek V3 to generate potential chain of thought and keep them short, because long chain of thoughts are not needed for this kind of questions to avoid overthinking. And for simple questions like hello, they don't need a chain of thought. Then they apply supervised fine-tuning for 2 epochs on those 800K total data points. And the final stage here is the reinforcement learning for all scenarios. They aim to improve the model's helpfulness and harmlessness while refining its reasoning capabilities. So for reasoning data, they use the same approach as R1 and for non-reasoning data, they focus on rewarding the utility of the final summary while minimizing the interference with the reasoning process to enhance helpfulness. This is because the main purpose is to make the final answer helpful. To ensure harmlessness, they evaluate the entire response, including both the reasoning and the summary, to identify and mitigate potential risks, biases, or harmful content. Identifying the reason on generating the harmful answers helps the researchers to understand the motivations or rationales on those behaviors and prevent it when it begins. And lastly, regarding the distillation, the base model they use are Queen models and Llama models. They only apply supervised fine-tuning to those models for convenience and to save computational overloads, because encouraging the models to develop reasoning capabilities simultaneously is more costly than using supervised fine-tuning. Okay, so this is basically the gist of their technical report. You can find the released models on their Hugging Face page, and I have included the link in the description as well as the link to the technical report. Thank you very much for watching.